What an intro. Right, folks, welcome. While this talk will be in English, feel free to ask your questions in Spanish. Pueden preguntar en español en cualquier momento. Esta charla es suya. All right, welcome. A little show of hands. Who here work as a data scientist, data analyst? You work with data? Awesome. Who works in the other side, in the ML infrastructure, ML ops, platform engineering? Awesome, great. Who uses Jupyter notebooks on a daily basis or have used Jupyter notebooks? Awesome. Who loves Jupyter notebooks? No. A few people. All right. So essentially in this talk, we'll discuss a little bit, some of the challenges with Jupyter notebooks, which is a very, widely adopted tool in the data science space. But before that, and for the benefit of the rest of the audience who didn't raise their hand, I will give a quick intro, ultra fast intro to ML, deep learning, and ML ops. I will miss a lot of details. So if this quick intro raises questions, feel free to ask questions at any time. Happy to help. And also we'll see how a platform kind of behind Jupyter notebooks can help bridge the gap between a notebook and production, right? Right, so let's get started. What is ML? What is machine learning? I think the best way to understand this is to see the difference between an ML application and a regular, let's say, software engineering application. On top, you will see, oh man, this is terrible. But on top, you will see kind of the structure of a traditional app. You have an input that is a set of instructions, right? The program is developed to know under certain conditions what to do and generate an output, and that's it, that's a program. But in the ML application world, the input is not command, not instructions, is data, right? And the whole point is to train a model that can learn from the data and generate predictions. From here, probably you can see some of the differences. Software applications tend to be better with the time, tend to improve with the time, right? You release a new patch, a new version, and the app is slightly better and better. But with ML models or ML-based applications, it's the opposite. If you don't do anything with your app, it will become less and less useful with the time, right? Because the input data is changing all the time. So I don't know who used a ride-sharing application to get here. InDrive, Uber, anything? I know you have used this in the past, for sure, right? And one of the key metrics of the services is the ETA, the estimated time for arrival, right? Your driver is, 10 minutes away from your home. That is the main metric for those models. But what happens if the car is going through a home, but there's a crash in front of them? Probably that will aggregate, that will add 5-10 minutes more to the ETA, right? So the model needs to react quickly to changes in the input. So that's one of the major differences between ML apps and traditional apps. And of course, you need to observe the quality of the metrics and the predictions all the time. By the way, this is a great book, pretty short, and it's great if you want to break into ML. Probably ML doesn't make headlines these days, it's all AI, but guess what? There's no AI without ML, right? So AI is kind of the whole set of disciplines in which you train a machine to accomplish tasks that typically require human-level cognition, right? But machine learning is a subset there where you focus on developing and training algorithms that can learn from data, and especially from unseen data, from data that the model hasn't seen before, and make predictions. And a subset of machine learning is deep learning. Essentially, it's called deep because it tries to mimic the way the human brain works with multiple neurons and multiple interconnections between neurons, right? And so it was developed using multiple layers, and all those hidden layers are what we call a neural network. So that's why we call it deep learning, but essentially it's kind of the same. How to develop a model that can understand complex patterns, complex relationship between things like language and images, for example, and that's why it's kind of is the discipline or the science behind LLMs and all this AI revolution, right? So if you want to really become good at AI engineering, there are two paths. You can be really good at prompt engineering, right? Building apps on top of pre-trained models, and that's fine. Or you can be really good at all the kind of machinery that is behind the models, and that pays more. And the other thing that is really key to understand here is that typically in ML, in machine learning apps, you have three phases. You have the training phase, you have a data set that has previously been annotated. So it's kind of the model goes to school, right? And the model sees, hey, if you see this example, this is the output we expect. If you see this example, this is the output we expect, and so on and so forth, right? That's training phase. Then you move it to the inference phase, where you expose the model to data that the model hasn't seen before. And you observe how accurate is the prediction, and you keep improving the model. And the next phase is serving. You serve the model, you make it available to another application or to your end user. And those are the three phases typically in ML. In AI, and specifically in deep learning, the inference and serving stages typically collapse into a single one, because when you're serving the model, at the same time you are doing inference. For example, let's say we are OpenAI, right? And we are making ChatGPT available to anyone in their mobile phone. So at the same time, you're serving the model, but the model is also seeing new data, right? All the prompts you enter there, most of the time is unseen data, right? So at the same time, you are doing inference and serving, and that's pretty specific to LLMs. So far, so good? Any question so far? Good, all right. So next up is, okay, what it takes to take a model, a nice scientific model, and make it a real product. Well, guess what? Around 70 to 80% of the ML models never get to production. That's public data. Different surveys throughout the years, a lot of research has arrived to the same conclusion. It's very hard to take an ML model that lives nicely in a Jupyter notebook and makes it a real working production app. This is only a subset of what is needed to take this fine model that extracts data and analyzes it and pass it through multiple stages, like training, as we mentioned. The trained model is stored in a registry, kind of a repository for trained models, and serve the model. This is so simple in theory that it can be done manually, and many companies, many teams today do this manually. Right? They use Python scripts. I don't know if you are one of those teams. Sorry if that's the case, but many of them that we have met before, they use Python scripts in Jupyter notebooks to develop, train, and serve models. And that is very hard to maintain. This is kind of the level 0 of the maturity model that Google Cloud proposes for MLOps. With the level 3, the highest level of maturity, involves many things. Probably you don't see all the details here. It can be even more complex than this, but the whole point is that this is kind of CI/CD, but for ML apps, right? In continuous integration, continuous delivery for software apps, the whole point is to release constantly, right? There are many benefits that probably you all know about releasing frequently. In ML, or in an ML pipeline, the whole goal, the main goal is to achieve continuous training. How frequently can we train the model? Because the data keeps changing. And as I mentioned, if you don't train your model continuously, the predictions will become less and less useful. And one big thing here that Probably it's not in the slides. Software engineering or traditional apps fail in a way that you understand that it's failing. For example, if the app is down, you get a 404, right? You get if there is an authentication error, you get a 403 or whatever. You get an error. But in an ML app, the model can be totally broken, but it still is working. It's still giving you predictions, probably really bad predictions, really inaccurate predictions, and it can be very dangerous depending on the use case. It can be very dangerous. Let's say it's an autonomous vehicle. If an autonomous vehicle, a self-driving vehicle, is wrong on the predictions, it could kill someone, or it could kill you, right? So it can be very problematic, and this is why it's not an understatement or overstatement to say that probably this is even more complex than shipping traditional applications. Cool. So you came here, and there was notebooks in the session title. So what's up with notebooks? What's wrong with notebooks? Well, there are a few things. So let me show you. Yeah, I think, can you see this? Folks down there, can you see this just fine? Okay. This is a math notebook that I reproduced. It's I don't know, probably you've seen this before. It's pretty famous. A guy, I don't know, 6-7 years ago did this in a JupyterCon in North America, and I reproduced this here. So essentially, it's a pretty simple example, right? You have a function that sums the input plus 2. And I'm sending, or I'm feeding the function with a number 2. So 2 plus 2 should be 4, right? But it's giving you, it's saying, no, it's not 4, it's 5, right? There's a song for this. I won't play it to not break copyright stuff. But there's a nice song by one of my favorite bands, Radiohead. 2 plus 2 makes a 5, right? And this is the case. You can make, yeah, thank you, EC2. You can make 2 plus 2 make a 5 with Jupyter Notebooks. Only that should give you an idea of how broken this is as a tool for data science. I just mentioned how critical is accuracy in ML and especially in LLMs. You saw in the previous talk that there are folks trusting LLMs to be therapists or doctors or stuff. But if we are developing those models in a tool that can do this, there's a problem, right? So the reason for this, why this works, I mean, I made a trick. If you see the numbers there, that's the execution count. You probably noticed the trick, right? I modify the function, right? And that's the last thing. I modify the function, but I didn't rerun the cell when you print the result. If I rerun the cell right now, it will give you a 4, right? But the thing is that Jupyter Notebooks run with a kernel, right? And this kernel has 2 main characteristics. First, it's a single Python process. You can have here 1,000 cells, and all of them will run in the same Python process. So far, so good, but if you stop your Jupyter server, Jupyter instance, if that process dies for some reason, you will lose the outputs, right? If you share this notebook with another team member, this team member will need to rerun the cells to regenerate the outputs, right? That's the first thing, probably not that problematic. But the second characteristic, which is the most problematic, is that the kernel doesn't enforce ordering. You can execute the cells in whatever order you want. And that's why you can produce these problems, right? Imagine if it's a long, very complex notebook, and you're not completely sure about the order of execution, you could produce very bad results. The good thing about notebooks is that you can easily share results. You can combine Markdown with code, so it gives you a well-documented piece of code, right? And you can also add plots, graphics, next to your code. So the feedback loop is pretty short. You have the code there, and you have the output immediately below, so it's easier to see the results. but it's not reproducible. And by reproducible, here we mean that if I share this notebook with someone else, with another team, with another company organization, can I trust that they will get the same outputs that I said that I got? Well, that's not the case. They are not reproducible, and those are not my words. Oh, yeah, it keeps coming. There you go. Christ. All right. There was a study from folks in 2020. Essentially, they analyzed hundreds of Jupyter notebooks in GitHub, publicly shared. And the question was pretty simple. Okay, I will download this notebook, and I will run it. And I will see if it produces the output that the researchers or the engineers said it will produce. 73% of the times, it didn't produce the results that it was supposed to produce. It was not reproducible. That's a problem. It's totally broken. So, yeah, that's why many people complain. It's so easy to write a nice model in a notebook, but it's very hard to take it to production. Who writes ML models in notebooks? A lot of people. A lot of people these days still do this for the reasons I mentioned. Many folks doing data science, probably it's not your case, but many folks I know doing data science, they come straight from academia. They have their shiny master or PhD degrees, and they just want to develop the best model on earth with the best metrics and ship it in a Jupyter notebook, and that's it. So it's pretty popular, pretty common, but the format is broken. So here I'm going to introduce an open source project that is not designed to fix notebooks. It was designed for a bigger problem, but in the road, it can also help with the lack of persistency that notebooks has. So this is Flight. Flight is an open source project. It's hosted by the Linux AI and Data Foundation. And it was born out of Lyft. I don't know if, well, Lyft is not available in Colombia, but probably if you have gone to the US, you can request a ride with Lyft. It's a competitor to Uber. And they have this problem of optimizing for ETA, for the most accurate estimated time for arrival in the app. Back in the days, there was Airflow, there were many other tools out there. So they were frustrated and they built Flight with a simple premise. Can we do this as close to Python native as possible, and also at the same time make it declarative and make it integrated with whatever infrastructure you have? So that's the essence. Right now it's being used by many teams to do all sorts of things. Spotify uses this today to process essentially the money they pay to the artists, right? So it's pretty core use case. It's the money they pay for the music. LinkedIn, if you use LinkedIn and if you see the recommended post or recommended connections, people to connect with, that's powered by Flight. This is public information. It's not the stuff that I'm making up. And this is only the people who have agreed to make it public. You will be surprised by the names who use Flight, but for some reason, they haven't agreed to make it public. HBO, the recommender system in HBO Max, uses Flight. And also Woven Planet, which is the autonomous driving research lab of Toyota, uses Flight every day. And the latest product was the Toyota RAV4, which has a self-driving mode that was entirely developed with Flight. And many more. These folks, the topology, they orchestrate with Flight to generate massive data sets, synthetic data, essentially. Ertera, this is a biotech startup. They develop early prostate cancer detection technology that is available in the Medicare US healthcare plan, powered by Flight, Stripe, the online payment service in the US, it's kind of necky here, but in the US, powered by Flight, and many more. Catio, they are developing multi-agent systems with Flight, it's over there. So it's kind of not a side project, not a toy project, it's widely used, and even these folks who send 6 scientists to the International Space Station with a device tracking the brain to understand how the brain works outside the Earth. The analysis of this is done with Flight. All right, so what's the point here? I just show you what it takes to take a model from nice isolated model to a product. This is just a pretty summarized version of it, of all the steps that will take to build this pipeline. So you have all the steps there. In Flight, what happens is that you just add a Python decorator, add task, and that produces many things. One of them is that each one of these tasks will become a container. Are you familiar with containers, Docker containers, OCI containers? Yeah, pretty much, right? A self-contained unit of execution. Every task will be a container by default orchestrated by Kubernetes, but it can be many other things. It could be a Spark task, it could be array, cluster, it could be many things. But by default, if you don't have the need for any other plugin, you could just orchestrate with Kubernetes. What happens here is that I mentioned that the 2 problems of notebooks, remember, is that you have a single execution environment for everything that lives and dies with your data, with your outputs. If you lose the execution environments, you lose the outputs. Here, you could say, well, it's the same. If each task is a container, what happens with the container dies? Well, probably it's not shown there, but Flight automatically connects with an S3 bucket, right? As object storage bucket, wherever you have it. It can be AWS, Azure, Google, your home server, wherever you have an S3 compliant bucket, it connects with Flight, and Flight will store your outputs there in a durable fashion. What I mean with durable? Flight will only report that the execution is done until it's sure that the outputs are stored in S3, in an S3 bucket, in object storage, right? Only there, it will kill, or the process will be done, the container will die, because we don't even need the compute environment anymore, but you have the outputs available. So the outputs outlive the execution, very different to what you have by default in a notebook. And also, the another thing that happens is each execution is automatically versioned. So you have a versioning system embedded in Flight, so you can reproduce a specific version and you are pretty sure that you will get the same outputs because it will retrieve the outputs from object storage. I will show you in a bit. So that's the whole idea, how to make this a durable system that outlives the execution environment or the compute environment, and how we can make it available to anyone writing Python code. So if you want to follow along at home, you can just go to this URL. It will open up a Colab notebook. Essentially, it's a Jupyter notebook, but hosted in Google Colab. And it has all the instructions for you to run what we will see here. In the spirit of reproducibility, you should get the same results we will see here, right? So let me go straight to the live demo. I mean, what could go wrong with a live demo? Cool. All right. So here is a few things. I will connect to a Flight cluster. Flight cluster sounds like complicated. It's just a single command, right? Flight CTL demo start. Can't believe it, 5 minutes. There we go. So, I will just say, hey, I will connect to a Flight cluster that is already running, already have a few packages installed locally, and this is the main thing. You will here declare the contents of the container image. If you have built containers before, probably you have develop Docker files. And if that's the case, you probably already hate Docker files. Here you don't need to even write Docker files. You can declare the content of the content you need in the image, in the container image, and Flight will build it for you, right? So you have here this, the task, and I have a task that performs data ingestion. I mean, for folks here doing ML, this is pretty simple. It's the infamous penguins data set. It's so common. But I will show you just how to train a simple model here that you can do all sorts of fancy things. So let's look at this. Is the add task decorator that I mentioned. The rest is just Python, right? It's just invoking a Python function that will download the penguins data set with a certain features, right? And I will just say or instruct my my notebook to connect to a remote instance or to a Flight instance and to run execution. It's taking some time because it triggered an execution. Flight has a UI, and you can see here that there should be, yeah, there you go. There's a running execution, right, of this simple task. It's right there. Probably it's already done or will be done in a bit. And it generated a version automatically. You don't have to integrate this with GitHub, SVN, or anything like that. This is automatically, anytime you make a change and you run the execution, it will generate a new version. So that gives you hermetic executions. There you go, it's done. I will look at the output. The output is essentially a path to a data frame where I downloaded the data set, the execution URL, whatever, and I will play with the outputs, right? I will do a print head on the data frame. That's nice. I will see the frequency for each penguin species in the data set, right? This is the power of notebooks, but with the durability of a system that preserves your outputs. Correlation between variables, yeah, that's nice. So I will split the data set between test and actually training, and I will define a couple of tasks, right, where we train a logistic regression, pretty simple model on the data set, and we define this workflow that connects everything together, and we will run the workflow here, right? In the meantime, you can see that I already had an execution. It generated the training set, the validation set accuracy. If you make a change, every time you execute, it will generate a different version, and you can pretty much, there you go, thank you. That's it. You can rerun any past execution from the version you have generated. So yeah, that's it. Recap. Without an external system, notebooks are broken. So Flight adds a state machine that makes your notebooks production ready. So feel free to go to Flight.org or the Slack community or get started with Flight. We are about to release the version 2 of Flight. What we just saw will be completely changed. So Flight will go fully async, no DSL, no workflow. If any Flight user here, there will be no workflow, no DAG, just extreme dynamism to build agents at scale. And yeah, we're hiring. If you want to take a look, union.ai/careers. Thank you. Any question?